Okay, guys, I hope you are able to get this. And if you're not, well, then you're not hearing me say that I hope you can get it. We should be about page 75 here in the book. We're going to start talking about motors. And motors is the opposite of a generator. If you look back at the definition of a generator, it's going to convert mechanical energy into electrical. Well, the motor is the opposite of that. And if you think about it, that makes pretty much a lot of sense because, we use a motor to do work. We use a motor to move our car. Um, Motors that make fans turn so that you get a breeze, etc., etc. But if you look at their configuration in the chapter, you'll see that they're very much similar to what goes on with a generator. Um, they work by what we call the motor principle. So if you look on page 74, underneath that highlighted part which says motors, it's the result of the interaction of magnetic fields. What we're doing, we're sending electrical current to that conductor, and it's causing something mechanical to turn. What causes that is that interaction of that north-south pole that you see here on the illustration. Um, as like charges repel, opposite charges attract. And it's that same thing that we use in so many different ways. You probably never even really thought about it. When you were a kid, you learned about magnetism and you put stickers on your refrigerator and things like that. But what that is, like a fundamental principle. The way things work, almost everything works in our world, and so we use that in all types of ways. It's important for us to understand the motor principle just a little bit so that we know that something mechanical is happening because of the interaction of those magnetic fields. And we're probably better off saying the interaction of those electromagnetic fields because those magnetic fields are induced from the flow of electrons, which is, as we remember, electrons are small and negatively charged, and that's that negative charge that's the key. If we can find something that's positively charged and then push a negative charge near that, or something that's negatively charged, then we can cause things to happen in a very predictable manner. So that's what we're trying to do here. So a motor, then, to say again, is going to produce some sort of mechanical motion. Now, where in our X-ray circuit might this be something useful is out there with the X-ray tube itself. We've got a mechanical piece of equipment inside that vacuum tube that needs to move. It needs to do something. So we're actually going to use the generator to induce power to that'll eventually make it to the X-ray tube and will induce a motor type or physical function for that X-ray, what we call the anode, to actually move. There's two different types of motors. Don't worry too much about this, but there's DC motors and AC motors. DC motors have what are called commutator rings, and AC motors have slip rings on them. And it's more, if you look on Figure 419, the AC induction motor, it's on page 76. That just means that it's able to maintain power supply to that motor while it spins. And probably for us, the easiest thing to think about right now, and probably the most important, is to think about that motor spinning or inducing something to spin. And in our case, it's going to be the anode on the X-ray tube. And I'll explain what that is in another chapter. It should be about chapter 5 or so. Yeah, under X-ray equipment. And so that motor is going to, because we're changing north-south poles back and forth really quick, or alternating north-south poles really fast, that is going to induce that rotor to spin and try to keep up with that. And what we want it to do is to spin somewhere around 2,500 RPMs. And I'll say now it's because of heat dissipation, and then I'll explain it later when we're actually looking at that in during class. Okay, because I've got an X-ray tube that we'll pull out and we'll pay attention to and we'll watch here. So I use the term rotor already, and if you see here on the illustration, and I think this is recording the mouse as well. The stator is or pardon me, the rotor is the interior part that's gonna spin, and when we watch our X-ray tube turn, or when you're out in the lab and you depress the prep button on the equipment, what you hear is a whirring sound, and that's this rotor spinning in here. What you're actually listening to are the bearings that are outside here somewhere that kind of whir and hum as they spin up to 2,500 or so RPMs. Give it a little, give a little or get a little off that. But it's around 2,500 RPMs. And that's what we actually hear when we're making X-rays. That's the mechanical noise, and it's because of this induction motor that we have inside the X-ray tube. And again, what I'll do is I'll pull this X-ray tube out and we'll watch it function, and it'll make a whole lot more sense. But that's inside the lab there. If you want to walk into the darkroom and look at that, it's sitting on a wooden box. As long as you don't, you're careful with it, go ahead and pick it up, place it somewhere where you can look at it or whatever in your free time, and then we'll get to it in the class period where we deal with X-ray equipment. Okay, but you'll notice on the outside of that X-ray tube that there's some really heavy magnets, and you see these out here in the illustration, and we call that the stator, which is outside the X-ray tube. So the rotor is inside the glass part of the X-ray tube, and the stator is actually the big heavy magnetic stuff with copper wrapped around it, which is outside the X-ray tube. And those two work in concert. We've got a sealed piece of glass that goes around here. It's sealed to maintain a vacuum for other reasons, which we'll get to. But we need some way to mechanically make activity occur inside the tube, and so a magnetic field will reach right through that glass, doesn't even know it's there, and will induce this rotor to turn when we activate the stator. It's really a simple principle. And if you've ever looked at your car alternator or at a fan turning, or we've got a fan in the lab too, it's essentially the same technology that's making this spin happen, and that's the really important thing that we want to see. All right, so now let's talk about electrical current. You'll see this next box here on page 76. One of the struggles that we have in X-ray is controlling the current that goes in there. In our X-ray circuit, we've talked about circuitry. We've talked about series circuits and parallel circuits. And a couple class periods back, I said we're going to have to manipulate both series and parallel circuits. And then we worked a little bit with the Ohm's law formula. And you should be able to do that to a point. And like I said, we're not going to wire houses. We're not going to be ridiculous. But what we're trying to do is gain some understanding about what's going on inside the X-ray circuit itself. And so what we got to do is we've got to take that current, which coming from the street, what we're plugged into in any facility, is some sort of alternating current. Sometimes it's three-phase, what we call high phase, or really good quality electrical current, and most likely at your house it's probably not so great. X-ray tubes X-ray circuitry requires that we have some three-phase units usually, but we've got single-phase X-ray circuits too, and I'll explain that again another time. And inside our X-ray tube, we've got various things in here, and you'll see there's a couple of them listed here: transformers and auto transformers. We'll also talk about capacitors, but as a separate power supply. Transformers, the job of the transformer, if you see on page 76, is to change the current. It's going to make the current, in our case, increase or decrease in voltage. And for us in X-ray, we do both. We need to have a transformer that will cause an increase in voltage, and also a transformer that will cause a decrease in voltage. So remember, when we use the term voltage, we need to think potential, because that's the potential energy that we're going to be able to use. And that means that sine wave that I've drawn on the chalkboard a couple of times, if we increase the voltage, that sine wave is going to rise higher. We're going to have a much more steeper hill. And remember, back, if you get on your sled and you're sledding down the hill, the steeper hill is going to make you go faster. So transformers manipulate the size of the hill. It's pretty neat. And there's two really different types of transformers. Broadly speaking, we'll say that there are, regular transformers which have two separate, or what we work through this process called mutual induction, and then an auto transformer that works through a process known as self-induction. You'll want to write down both of those, mutual and self-induction, and which one goes with which. And then you also need to put the definition of mutual induction down in your notes. Mutual induction requires two different pieces. We've got a primary and a secondary, and they are not physically connected. There's not a piece of wire connecting one to the other. Rather, mutual induction is where the magnetic field from the primary side interacts with the conductor, which is on the secondary side. One of the things I told you early on in this class, just a few class periods back, was I said anytime a magnetic field interacts with a conductor, a current is induced to flow. Now you notice I slowed down and I tried to pronounce all that very distinctly, so you might want to rewind and get that. Anytime a magnetic field interacts with a conductor, a current is induced to flow. And if you look at the transformers, an illustration of a transformer, if you want to Google that, or if you want to turn to page 79 and look at that air core, maybe in the upper left, it's the easiest one to see, you'll notice that those two pieces of equipment are not attached. However, those little dashed blue lines that are coming out of there, that is the interaction of the magnetic field. And the other thing that we have to remember about transformers is that magnetic field comes from the movement of electrical charges. So, if we have a bunch of electrons, get it, electrical charges, moving down the left side of that transformer that's marked A, air core, top of page 79, if we have a bunch of electrons crawling around the outside surface of that on the shorter side, there they will produce 90 degrees opposite to their direction of travel a magnetic field which will, for lack of a better word, cut through the larger coil of wire or filament on the right. And so those magnetic fields will be slicing through the metal or the conductor on the secondary side or the right side. So we got primary on the left, secondary on the right. Since because of how they have to work this way, since they are the product of an alternating current, that magnetic field will increase and decrease in intensity. So it's going to get bigger and it's going to get smaller. And if you could see me, you would see my hands going wider and then closer back together. As that field gets bigger, that magnetic field will cut through the secondary side. As it cuts across that conductor, remember what I said, a magnetic field cuts across the conductor, a current will be induced to flow. And then as it retreats, as it gets smaller, the same thing happens. So although there's no physical contact between the primary and secondary, there is a magnetic contact. And that's going to induce current to flow on the secondary side. Now, I'll say again, I'm probably getting ahead of myself, but I'll say again that at the top of page 79, the one that's marked air core, we've got a short one on the left and a long one on the right. That means that this is what we would know as a step-up transformer. Anytime we go from smaller to bigger, we're increasing voltage or increasing potential. And for example, you will find a transformer that is illustrated much like this one inside our X-ray circuit at what we call the step-up transformer. And that's where the voltage from the wall where your X-ray machine's plugged in becomes kilovoltage, which is going to be used to make photons later on to X-ray your patient. So, we talk about 50 kVp or 100 kVp or whatever you guys are using for hands and whatnot now. It's probably 50 to 60 range, 45. That kV really means thousands of volts peak. And that thousands of volts does not come from the plug-in in the wall, but comes from this step-up transformer. So that's what we're talking about. There is an opposite one known as a step-down, and all the same things happen except the voltage decreases and the amperage increases. And we use one of those inside our X-ray circuit as well. So we'll get to that. And then this auto transformer changes voltage, but it does so by itself. It works with this process called self-induction. And if you think about it, as those electrons are crawling around the outside of that conductor, they are released. They are accompanied by that magnetic field, which also will cut through the conductive material above and below their path. And so that creates a self-transformer type of situation. We call that auto-transformer. We're going to use that way to the left for a different thing. We use the step-up transformer, which I described. The auto transformer we're going to use to adjust the voltage of the incoming AC waveform so that we can eventually use it to create KVP later. But that's not what it's for right at this point. It's just going to adjust or smooth out the voltage for us. But like I said, I'm probably getting ahead of myself. And then we also use capacitors, which a capacitor, just like a battery, a capacitor stores charge, but unlike a battery, a capacitor will release all of that charge all at once. So the capacitor the capacitors that we might use in X-ray are going to be used for different types of power supplies for X-ray units, and I'll talk more about that here in just a little bit. One thing I want you to note, page 78 in heavy black letters, and I highlighted it with a highlighter in my book. Midway down, left column, page 78. All transformers must operate on alternating current. That's a requirement. They have to provide they have to provide the establishing and collapsing magnetic field that induces the voltage changes in the secondary coil. And I explained to you why just a few minutes ago. So one of the things you need to have down in your mind is all transformers require AC current to operate or some sort of moving parts. I explained how the AC currents work in there on that air core on page 79. If we had a DC current, what you would see are electrons swirling around the outside on the left as before, but their magnetic field would stay constant. It would just be one size. What we want is for that magnetic field to cut through the conductor. So if that magnetic field stays constant, then what we would have to do is separate the primary and secondary side somehow mechanically. Move it in and out from each other. And then that'll cause it to work. Sounds like to me that's a lot more complicated than just having AC. So for the most part, AC current is required to use a transformer or to make a transformer function. There's different kinds of loss in there. You probably just need to know the definition of this. I squared R loss or copper loss, that's just the resistance. There's always going to be some resistance. Remember we said we need voltage, amperage, and resistance. There's always going to be some resistance to the current flow. We call that I squared R loss. And that just means that transformers lose some of their efficiency. We also have hysteresis or lagging loss. That's where that constantly changing magnetic field, it takes a few microseconds for that to catch back up. And then eddy current loss, that's lost from the core. Those three things can happen that will affect the efficiency of your transformer. But again, I'm not going to spend a great deal of time talking about that because the thing about transformers is they are something we need to understand at a basic level, but we don't need to get too crazy about it, okay? We just need to understand that transformers require AC power, what the primary secondary side is, what they do, those sorts of things, and then we just stop. We need to get nuts about it, okay? So some of these things that I just talked about here are displayed on the slide. Mutual induction, and we got to remember about Ohm's law, which I just said. So I've said these things. We've got two different types of transformers here, step up and step down transformers. We also have the transformer law. And to set this up, this is real similar. Remember we looked at the inverse square law recently. And to set this up, you just have voltage secondary over voltage primary equals the number of turns on the secondary side over the number of turns on the primary side. So it's secondary over primary on both sides. And again, just like, no, I think I probably said the wrong, just like the inverse square law, we've got something over something equals something over something. But unlike that, they're both secondary over primary. Whereas on the other one, on the inverse square law, we were talking about I sub 1 over I sub 2 equals D sub 2 over D sub 1, both squared. This way, it's V of S over V sub P equals N of S over N sub P. So we keep both S's on top, both P's on the bottom. And you just got to have all three, or at least three of those things in there so that you can figure out what number 4 is. And the question might be something typical. It'll say, the number of prime, or what are the number of secondary turns if the primary turns are this, and et cetera, et cetera. And then you can figure out either your voltage or your number of turns or whatever you want. There is a link here that I'd like for everybody to take a second to go look at. It displays how the transformers operate, and what you can do is you can manipulate the number of coils on the secondary and primary side, and take a look at how transformers change the output voltage based upon what the input is, the number of coils are. That, folks, whenever you manipulate those turns in there, that's exactly what you're doing when you change your kV from 40 to 50 or to 60 or to 70. You get it? When you manipulate your kV, what you're actually changing in real time is you're changing the voltage. And you'll go from 40 volts to 50 volts, and that's your incoming primary voltage. Your outgoing secondary voltage will then be 40,000 volts or 50,000 volts. And it's a little different ratio than what I just said, but that's easy enough for us to understand. We come in one side, we go out the other side many thousands of times greater. And we need those thousands of volts or kilovolts in order to induce the proper energy of our X-ray photons. Okay, so let's look here at these transformers that we've got on on this page. The I squared R loss, hysteresis, and eddy current. The best one to use, and the one that's most often used because it's most efficient in X-ray, is the shell type transformer. So if you didn't remember anything about stuff like that, look at the shell type transformer as being the one that's used most often. And you can see that it's in blue just below that. Tells you a little bit more about it. X-ray generators use laminated core shell type transformers, the most common type in use today, and that's because least amount of loss. And hey, that's what you need to understand, and you're done. Okay. And then I talked about auto transformers, and they're connected in a series, and you see sort of an illustration here of an auto transformer. We've got a single coil, and if you look at that on this side, a single coil. We're not considering what's going on over here just yet, because really this one is two coils, right? So let's not worry about that. Let's just look at this one, and this is on the far left of our X-ray circuit. Sorry, this is on the far left of our X-ray circuit, and what we've got is a switch here where you are saying, I need 100 kV. Click, 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 and we'll switch that over to 100 kV. And this will make sure that the incoming AC voltage is sufficient so that it goes out into what we call our step up transformer and will cause something to happen. On this illustration, this happens to be a step down, just so you know. Too many coils here, less coils here. So we're going to step down in voltage. In A, like I said, that's a step up transformer. More coils on the secondary, less coils on the primary. And we use those, again, those auto transformers to help make sure that the electricity that comes in from the street is of sufficient. My better illustration. Let's go back. We have to have AC in order to make these transformers operate. All three of these that you see here in this circuit have to have AC current. But X-ray tube does not like AC. It is a unidirectional tube, so it wants to have DC. So in order to change that AC to DC, we send our electrical signal, once it's been transformed and increased in potential, we send that through what we call rectifiers. And, make a bad pun, these actually rectify the situation. They take AC and make it DC, which means it'll be always on. And it's truly not direct DC, but it's close. And so we use these things. We have to have at least 4 in our full wave rectified unit. You can get away with 2 in your half wave rectified unit. And what we'll draw, I guess, is the best way if we put this on the board, is a half wave unit will show positive pulses. If you flip your book back to, well, let's see. If you flip your book back to page 94, in the next chapter, you'll see current A and current B at the bottom on figure 5-5. A standard AC configuration will be A, where we have an increase and decrease or a full waveform. That's what transformers need to operate. But our X-ray tube doesn't like that. An X-ray tube would rather have all positives in there. So a simple half-wave rectified unit or a full wave rectified unit on in B there will flip all the negatives up into the positives. A half wave unit, if you want to know what that looks like, a half wave unit will be instead of flipping all the negatives into the positive zone, those humps, it'll just ignore them. So what we call that is a self wave or half wave rectified unit, which really means there's no rectification at all as far as the tube's concerned. We'd like to have at least a full wave rectified unit, and you'll notice there in B on figure 5-5, what we've done is got twice as many positive pulses now of electrical energy as what we had in A. So we're doing twice as much work there, or we're going to produce twice as many X-ray photons from that. What we're trying to do with our rectification, just go ahead and turn to page 96, and you're going to see B, figure 5-7B. What we're really trying to do is rectify that and then get three separate incoming AC waveforms so that we've got a very small amount of voltage ripple. You see that there on the right? So what we have is a full wave rectified three-phase unit. So the power never drops to zero. And again, I know I'm getting ahead, but it's hard to talk about one and not talk about the other. So just understand for today that rectification is the process of changing AC to DC, and that's what we're doing here. How it does that, these rectifiers these days use what we call solid state diodes. Bottom of page 81 in the bold. I'm not going to read it to you, but it shows you how it allows electrons to flow from the N to the P side, or what we call the P-N junction. P-N junction. And that allows, on page 82, that allows current to flow sometimes and not flow sometimes, and then it will change the shape of that waveform. We use silicon or things like that to help do that. And if you look on figure 426, there's a little bit more discussion. There's where you can see that. I'm going to be honest with you and tell you that you probably ought to know P-N junction, at least at some point for your registry. This might be something that you're asked. But I don't think you need to get so detailed in there that you try to describe that. Just understand that sometimes electrons can flow and sometimes they can't, and that'll change the silicon used there will change the direction or the shape of the waveform, which will cause the negative to disappear and flip up into positive, and we've rectified the unit. Truly, that's as deep as we need to get. We want past the transformers, we want to rectify our waveform because that X-ray tube desires that DC current. And again, remember the definition of rectification is to change AC to DC. What we're trying to do, let me flip past. What we're trying to do is change the waveform so that we get what we call thermionic emission, which is one uses diode, one doesn't. Okay? Same thing. So that's why I kind of just slash them together, half wave and self. So saying all that takes us here. I want to make sure that you've got in line, or that I've said to you that on page 83, thermionic emission, space charge cloud. Both of those are in blue. The definition for the cathode is just above thermionic emission here on page 83. Make sure that you pay attention to that because we're going to talk about that. Just below that word, the term space charge cloud, is the definition for the anode, or what it is, which I already said as we talked about this today. Turn the page. Notice figure 429 is what it talks about, and it says, remember that electron flow will always be from cathode to anode, and so conventional electric current will be from anode to cathode. Okay? Electron flows one direction, electrical current flow is the opposite direction. Don't get too crazy about it, but that's how it works. Don't worry. And then we've used these terms here on page 84, half wave and self rectification. And then if you, and I think I talked about those probably sufficiently. And then full wave rectification. Let's look at the illustration on page 86. You can see with four, and by the way, we talked about half and self wave. We need one or two diodes or none to make that work. Here's probably a pretty good thing to remember is if we go full wave rectified, we need to have at least four rectifiers. Now, these rectifiers that are drawn in here are in no way related to what they actually look like these days, but still we illustrate them like that. In order to have a full wave rectified unit, we have to have four rectifiers in there to work. And there are 16 steps to illustrate the current flow. Not going to read them all to you, but they're numbered for you. And if I remember right, in your workbook, this might become useful to you later. Pay attention here at the bottom of page 432, or bottom page 86, figure 432, that rectified area is blown up bigger. So we've got our three transformers, we've got our incoming AC, we've got our exposure switch and all that stuff. Once we get past that, what we're really looking at are the rectifiers and the X-ray tube itself. And we want to have a current flow like you see in B, where we're not missing any steps, we're not skipping anything. We've got a consistent current flow going through the X-ray tube. Still, this is not the best. And when we get into the next chapter, we'll talk about how we can take single phase full wave rectified circuits and we can flip everything up so that we make, like I said on page 96, three phase rectified units. That's figure 57B. That's much more what we want to see coming through our X-ray tube. What that will mean is that's a constant potential X-ray tube. An even better illustration of that's on page 100. If you flip to page 100, you can see as these currents get less and less variable. We go to the right, we get much less voltage ripple, and we produce much better kV and a much more consistent X-ray beam all the way across. And like I say, I'll explain this as we talk about it. Put that in context with, on page 102, the capacitor discharge, where we produce a whole bunch of good X-ray to start, and then it drops off. And it drops off pretty quick. And we'll talk about that in the falling load generator and things like that. But make sure you know your definitions for those things. Full wave, half wave, rectification, half wave, or self-rectified. Don't memorize all 16 of these steps here on pages 86 and 7. Just read them and look at the illustration as you read each one, and that will help you to get this kind of all put together. Okay? We're going to have a test when I get back. The test will be spread out from chapters 2, 3, and 4. And I'm going to ask you questions about the stuff that we've talked about in class. And these are going to be concept or application type questions. Probably not a lot of memorization, more than you need to remember and understand the relationship between positives and negatives and opposites attract, mutual induction, things like that. I will also make up some math problems that we're going to work in there. I guarantee you, inverse square law will be on that the same way that we did it. Nothing. I'm not going to try to trick you. And the other thing is going to be the Ohm's law. Be prepared to work out two or three of those. Maybe the difference between a series and a parallel circuit. Specifically, we talked about resistance as it relates to those two. So remember, parallel circuits have much, much less resistance because it's got more one way for the electrons to flow. And be prepared to work out RT, or total resistance, in a parallel circuit, and then answer a regular inverse square law question once you've done that. Remember how to do the total resistance over there. So practice with that. I've been talking for 35 minutes on this, which is a long time for you to sit and listen to me online. I know that. And then when we come back, we'll take a test. It's going to be around 50 questions, mostly multiple choice kind of things, and then those problems at the end. And I'm feeling right now like I'll have about 5 or so problems at the end, maybe no more than 7 or 8, but no less than about 5 on there. Everything will be worth 2 points. And questions, you can email me, pbarger@sehosp.org. Just email me, and I check that, as you know, about once a day. And I look forward to seeing you guys when I get back. Take care.